Swayam Prabha. Digital India. Educated India.
Last lecture we looked at a particular problem on a frame which was loaded, and we saw how to develop the equations, and then I spent some time looking at how to solve that particular problem, and I promised that today I would start off the lecture by actually giving you the solutions. I hope you've had an opportunity to look at those solutions, and this is the final solution, which is the equations that I looked at. Remember that this was the ABC frame with a 100 kilonewton load here, 50 kilonewton load here. Okay, R1 and R2 were the two degrees of freedom, displacements corresponding to the degrees of freedom. And when we solved for R1 and R2, we got R1 equal to minus 2000 by 3 EI, which essentially means that R1 is 2000 upon 3 EI downwards. Okay, R2 was minus 150 upon EI, which essentially means R2 is equal to 150 clockwise. I hope you've got these answers too. If you have, pat yourself on the back, because you have understood the displacement method reasonably well. Okay, now if you substitute, now that you know R1 and R2, if you substitute them back into the equations, into the member relationship, member end moment relationships, then you get MAB equal to minus 60 kilonewton per meter, which essentially means MAB is clockwise 60 kilonewton per meter. MBA is minus 90 kilonewton per meter, which basically means MBA is clockwise 90. MBC is plus 90, which essentially means it's counterclockwise. And MCB is minus 80, which means it's clockwise. Okay. Now these can be obtained directly by substituting these values into the equations for MAB, MBA, MBC and MCB. Okay. What does that mean? Once we have found those out, what do we do? Next is the solution. I had actually given you the expressions for last time I derived the expressions how to get the support reactions. In fact, I listed out the expressions for the support reactions in terms of, if you remember, 50 plus HA is equal to HC, and HA is equal to minus of MBA plus MAB upon 10. Having substitute MBA and MAB into for HA, we got that HA is equal to 15, therefore HC is equal to 65, and these are the support reactions. Clockwise moment of 60 kilonewton per meter here, a vertical reaction of 100 kilonewtons, a horizontal reaction of 15 kilonewtons, and a horizontal reaction of 65 kilonewtons in this direction clockwise. These are the support reactions. Once you know those, you can always draw the bending moment diagram, and this is how the bending moment diagram looks like. Linear here, continuous, here, this is superposed on top of this, and so this over here is at the center of the beam is 115 kilonewton per meter. At the end of the beams it's 90 and 80 here, and 90 and 60 here. This is the sense of the bending moment. This is tension on the top, on the left hand side. Here tension is on this side. Here tension is at the top. Here the tension is at the bottom. Here again the tension is at the top. Okay. So I hope this is exactly what you have got from your solution. I just gave you the solution to this particular problem. Now what we are going to do is remember this solution. Okay. Interesting to note here is that almost everywhere the maximum, what is the maximum bending moment here? Maximum bending moment at on the left hand, on the right hand side is 60, on the left hand side is 90. Here on the top it's 90, on the bottom it's 115. Fairly uniform things. And what are the displacements? Displacements are 667 upon EI and 150 clockwise, downwards and clockwise. Okay. Now let us look at what happens to that particular problem where all that we have done is taken this and made it into a, we've removed the fixity here so that this becomes a hinge roller. Okay. By the way, before I end this particular problem, I want to tell you that this actually is the part of a particular problem that we solve in general. This is actually the solution to this problem. This portal frame problem with vertical loads of 100 uniformly distributed and equal and opposite lateral load of 50-50, essentially using the fact that this structure here again, this would be 8, 8, this would be 10 and this would be 6. This particular problem, if you look at this particular problem, this is a portal frame. Okay, and this portal frame actually by using symmetry can be simplified to this particular problem. So this particular problem that I am solving, although it does not look like a real problem, is actually a very real problem. This is a solution to this problem using symmetry. Okay. I'll take an opportunity to discuss this particular topic of how to use symmetry to make structures simpler so that they have lesser number of degrees of freedom is a topic that I'll take up later, a little bit later in the particular course. Okay. So remember that this problem is actually not a problem that is from just like that constructed. It is actually a real problem. Okay. So now we come to this problem, the next problem that we have. If you look at the next problem, this is the problem. Identical loads, the only thing that we've done is we've removed the fixity over here so that the moment at this point is 0, so that it becomes essentially a hinge roller support. Fixed support, hinge roller support. In this particular case, what is the difference in the solution process? Well, actually, AB member continues to be a fixed member because it is fixed at one end and continuous at another end. However, BC can now be made into a modified fixed hinge member because here it's continuous, so it's fixed, and here this is an end support where we know that the moment at this particular point is equal to 0. Okay, so that particular thing makes it BC to be a modified fixed hinged member. Okay. So let's see how we proceed with that. Well, we already know that this is a 2 degree of freedom. There is a third degree of freedom, which is the rotation at this point. But since we are considering the fact that the moment at this point is 0, this is not an essential degree of freedom. And so we are left with 2 essential degrees of freedom in this particular structure. Okay. So having identified the 2 degrees of freedom, the first step is first to write down the member force deformation relationships. So we look at the member force, and AB is a fixed member. So MAB is equal to 4EI by 10, L is equal to 10, so it's 4EI upon L, theta AB, plus 2EI upon L, theta BA, plus fixed end moment at AB. Now since there is no load in member AB, obviously the fixed end moment is 0. Okay. Then MBA is equal to 2 by 10 theta AB plus 4EI by 10 theta BA plus fixed end moment at BA, which is also equal to 0. Okay. So that is the member force member relationship for MBA. Where note that again theta AB and theta BA, the way we have defined it in this particular equation, actually turns out to be, what are theta AB and theta BA? Remember that these are the rotations of the tangent from the chord joining AB. Remember that. Rotations of the tangent at A and B respectively, considering the rotation from the chord joining A and B. Okay, remember that. I just wanted to just tell you that this, just to remember that that is the solution. Okay. Now here for BC, since BC is a modified member, so MBC is equal to 3EI upon L. L is 10 because 8 and 6 10. Okay. Theta BC plus fixed end moment at BC minus fixed end moment upon 2CB. Remember this particular thing. Here, what are these fixed end moments? These are the fixed end moments in a fixed beam, subject when the load is. Okay. Remember that these two quantities we had evaluated last time. This had turned out to be plus 100 kilonewton per meter, and this had turned out to be minus 100 kilonewton per meter. So when you substitute that into this equation, you get 150 kilonewton meter. Okay, and therefore MBC becomes equal to 3EI upon 10 theta BC plus 150. MCB we know is equal to 0, and theta CB we don't need to know because we have condensed out theta CB. Remember that theta CB is not equal to 0. Theta CB is not equal to 0. Remember that. In the modified fixed hinge, theta CB is not equal to 0. However, we consider the fact that MCB is equal to 0, and so theta CB can be statically condensed out, and we only are left with theta BC. Theta CB is not an essential deformation quantity required to define the force member relationship in BC. Okay. So we've got relationship for MAB, MBA and MBC in terms of its member end rotations. Okay. Remember that this one theta BC is also from the chord to the tangent. Okay. So this we have done. What's the next step? The next step is to find out the kinematic relationship. So let us look at the kinematic relationship. What's the first one? First one, we put R1 equal to 1 and R2 equal to 0. And the second one, we put R2 equal to 1 and R1 equal to 0. First and foremost, for this one, this is simple. So it turns out to be this way, and this is this way. Here, this is equal to 1 and this is equal to 1. So therefore, what we have here is that theta AB is equal to 0. For R2 equal to 1, theta AB equal to 0. theta BA is equal to 1 and theta BC is equal to 1. These are the only essential degrees of freedom that we are interested in, and we have evaluated them. Note that theta CB does not have to be equal to 0 because this is a hinge, and we acknowledge the fact that the moment at this point has to be 0, and we don't need to find this out. Okay. Now what about this one? If you look at this one, note that the displacements of the points remain exactly the same as we had computed last time. So this is 3 by 4, and if you look at this, so and the displaced shape looks in this way. Remember that here R2 has to be equal to 0. So the tangent at this point has to remain straight. Similarly, the tangent over here has to remain straight. So this goes. But over here, it does not have to remain straight because there is a hinge. Okay? So this is 1, this is 3 by 4, and this one you can compute is going to be equal to, remember last time we had done it, that if this is 3 by 4, then this is going to be equal to 9 by 20, and this is going to be 4/5, so that is 16 by 20, 9 by 20 plus 16 by 20, we had evaluated that this was equal to 5/4 from here to here. Okay, so if I draw the chords, because ultimately it is the tangent from the chord, so my chord goes this way, and this is my angle. This angle, if you look at it, is equal to 5 by 4 divided by 10, so it's 5 by 40. This one, this angle is equal to 3 by 40. This angle is equal to 3 by 40. 3 by 4 divided by 10. So these are our rotations, and therefore, if you look at it, theta AB is equal to, from the chord to the tangent anticlockwise, so it's plus 3/40. Theta BA is equal to, from the chord to the tangent anticlockwise, so positive 3 by 40, and theta BC is equal to, from the chord to the tangent is anticlockwise, so it's minus 5 by 40. Note something very interesting, that these values, if you look at these values, and if you look at these values, the fact that this point has become a hinge and not a fixed roller, it is a hinge roller and not a fixed roller as earlier, has nothing to the shapes, excepting for the fact that at this point you do not have zero rotation. Instead, you have zero moment. Okay, so in other words, in the earlier case it would have gone like this and gone like this because this cannot rotate. Here also this would go like this and then come like this because it cannot rotate. But as far as these values are concerned, they don't change at all because the tangent and the chord remain exactly the same. Okay, so therefore these things are not determined closely by the fact that this fixed roller has become a hinged roller. Okay, so the point that I would like to make is that the kinematics definitely depends on the support conditions. However, if we change a fixed support condition to a hinged support condition and keep the geometry the same, it has no effect on the kinematics and on the overall kinematics. Of course, as I said, the displaced shape may look different because the displaced shape, if it was fixed, it looks like this and it would look like this. However, as far as the kinematics is concerned, that is the relationship of the member end rotations with the degrees of freedom of the structure, they are no different from what we had evaluated last time. Okay, so this is an important point to note, that kinematics is essentially driven by geometry rather than by changes in support conditions. Okay, of course, one thing is there, in this particular case it has not changed. Why? Because the support condition change has actually introduced a degree of freedom. However, because we have used the modified method, okay, we have the same number of degrees of freedom, and for those degrees of freedom the kinematic relationships remain the same. However, if we had not used the modified beam, then we would have had another additional degree of freedom, and then of course we would have to do the kinematics of that degree of freedom. Remember that. Okay, so that's the point that I am trying to make to you. Okay, having done that, let us now write down the relationship for, and if you look at the relationship for AB, since the kinematic relations are the same and since the kinematic relations are the same and the member force deformation relationships are the same, so I have written down MAB and MBA, they are identical to what we had computed when the C support was fixed. It has no bearing on the member and force deformation relationship in AB, and therefore I have just written down the value of MAB, which of course incorporates that theta AB is equal to 3 by 40 R1 plus 0 R2, and that theta BA is equal to 3 by 40 R1 plus 1 theta R2. Okay, if you substitute those into the force deformation relationships, you get MAB in terms of R1 and R2 in this manner. Similarly, if you substitute again theta AB and theta BA in terms of R1 and R2 into the member end deformations, you get this MBA. This is identical to the previous problem. No change. Now let's look at BC. Now BC, because of the fact that C is a hinge, we had to write a modified member and force relationship, which only relates the moment at BC with the theta at BC, because we incorporate the fact that MCB is equal to 0. Okay, so if you substitute that, I have substituted theta BC. Theta BC, if you look at it, the kinematic is minus 540 R1 plus 1 R2. So if I substitute that into this, okay, and rewrite it, I get MBC is equal to minus 3 EI by 80 R1 plus 3 EI by 10 R2 plus 150. Okay, so these are our relationship. Note that this relationship is different from the previous problem. Why? Because BC in the previous problem was a fixed member, whereas in this particular problem it has become a fixed hinge, modified fixed hinge. Okay. Now, so we've written MAB, MBA, MBC in terms of R1 and R2. What's our next step? Our next step is to write down the equilibrium equations, and for that we will take help of our virtual work principle, the principle of virtual displacement. Okay, and to get the first equation, see, we have two unknown displacements, and therefore for the two unknown displacements we essentially need to write down two equations. Okay, and the first equation, the virtual displacement pattern, is R1 equal to 1 and R2. The bar actually gives the fact that they are virtual. Okay, this is a virtual displacement pattern, and if I substitute those in and put that, you will see that the external virtual work is 50 kilonewton is undergoing a 3 by 4 virtual displacement. So real force into virtual displacement is the virtual work. That's the external virtual work. The internal virtual work is going to be equal to MAB into theta AB bar plus MBA into theta BA bar plus MBC into theta BC bar plus, now MCB is 0, so 0 into theta CB bar plus 50 into 1. That's the reason why we have no interest in finding out what theta CB bar is, because we're going to multiplying with 0, so who cares? Okay, so we only need to know theta AB and theta BA and theta BC, and that we know. In terms of R1, that's 3 by 40, 3 by 40 and minus 5 by 40. So when I substitute MAB from the previous equation and multiply it by this plus MBC, which is this multiplied, plus 50 into 1, this is the reaction, support reaction due to the member load of 100 kilonewtons. Okay, that, if you remember, I had told you, is something that you have to consider, and that is the support reaction. That goes up by 1, so therefore the virtual work is 1. Now obviously the virtual work equation says virtual work external is equal to internal, so all we do is we take this and equate it to this. So if we do that, what happens? Now I've actually gone and multiplied all of those, and this is the work done by MAB, this is the work done by MBA, this is the work done by MCBC. Okay, so this is the external virtual work. So this is my equation, and if I plug in these, if you look at it, this is 8,000, 8,000 and 3,200, so LCM is 16,000. If I put that, this becomes 54 plus 54 plus 75, that's R1, and then plus 6 plus 12 minus 15 upon 400 EI into R2 is equal to, now this is 75 by 2, so by 4 it will become 150. This minus comes here plus, and this 50 goes here, becomes minus 200. So substituting all of those, what I get is, this becomes 183 upon 16,000 EI R1 plus 3 EI upon 400 R2 is equal to 25 by 4. Now please note that these are simple numbers, and that is the reason why I'm actually going to this trouble. Otherwise, as far as you're concerned, you can actually take out these and make them into fractions and do the solution, and you'll get something else. Okay, I mean, you'll get the same thing, only thing is that these will be in fractions, this will be in fraction, this will be in fraction. In decimal points. Okay, it doesn't matter. I've done it this way because in this I could do it. In some other particular problem, I might actually, since it just gets too complicated, I might actually just calculate on the calculator itself and put down in decimal engineering digits. Okay, so this one I have kept it this way. I leave it up to you to do it any which way you want to. Now that's the first equation. Now the second equation, for the second equation we need a completely independent virtual displacement pattern so that we can get a independent virtual work equation. Note, that I cannot highlight enough that to get two independent equations, you require two independent virtual displacement patterns. And that is the reason why, since getting independent virtual displacement patterns is that hard, what we tend to do is we know two independent virtual displacement patterns automatically. They are first the one where R1 is equal to 1 and R2 equal to 0, and the second one where R1 is equal to 0 and R2 equal to 1. We know that these are independent patterns. Okay? As I had told you earlier, you could take anything else and get, as long as you use two independent patterns. Because if you use two independent patterns, then and only then will you get two independent equations for which you can use to solve for R1 and R2. Okay? I use obvious independent patterns, and that's why I'm using one R1 equal to 1, R2 equal to 0, and the other one R1 equal to 2, R2 equal to 2. So for R2 equal to 1, the 50 kilonewton does not undergo any load, so the external virtual work is equal to 0. Internal virtual work is MAB into theta AB, which is 0, MBA into theta BA, which is 1, MBC into theta BC, which is 1, plus 0 into, we don't know what it is, but again 0 into anything is 0, so we don't care. And this is the work done by the 50 kilonewton because it does not undergo any load. So if you put this in, you get this equation, which is again, remember I told you that if you use the rotational kinematics, you essentially get back the equation that you would get by taking the equilibrium of joint B. Okay? Now substituting for BA and BC into this, and then putting terms together, what we get is 3I upon 400 R1 plus 7EI upon 10 R2 is equal to minus 150. This is my second equation, and I know that this is independent because my virtual displacement pattern is independent of the other. So now I write down the two equations, and if you write down the two equations, this is what you get. Look at this. This is my first equation, which is 183 EI upon 16,000 R1 plus 3EI 400 plus R2 is equal to 25 by 4. And the second one is 3I upon 400 R1 plus 7EI upon 10 R2 is equal to minus 150. So I've written these equations in matrix form just to be able to solve it, and therefore R1 and R2 will be the inverse of this into this. The inverse of this is written in terms of 1 upon the determinant. So determinant 1 upon the determinant is this. The determinant of this is 1272 EI upon 160,000. So inverse is this. And then the cofactor of this is this. The cofactor of this is this. The cofactor of this is the minus of this. The cofactor of this is the minus of this. Note something. Again, like last time I had said that this matrix is symmetric. Okay, again you see that it is symmetric. Okay, the reason for it to be symmetric is, understand what is this. This is the force at a particular point that gives the displacement at another point. Now, by the Maxwell-Betty reciprocity theorem, you know that the force load at one point that gives a displacement at another point is the same as the load at the second point giving the same displacement at the first point. And this is essentially because of that reason. Remember, when we're using the force method, we got that the flexibility coefficients were the same. Well, these are known as what are known as stiffness coefficients. What is stiffness? Stiffness coefficients are force to produce a unit displacement. That is stiffness. What was flexibility? Displacement due to a unit load. This is load required to get unit displacement. So you can see that flexibility and stiffness are actually the opposite of each other. And if you take a single spring, the flexibility of the spring is equal to 1 upon the stiffness of the spring, the stiffness constant. So the flexibility constant is equal to 1 upon the stiffness constant. That's how it is. Okay, anyway, so this goes that this has to be, they have to be the same. Okay, if you don't get them to be same, you have done something wrong somewhere. Anyway, so having got this and putting this in, I get R1 is equal to 691.824 upon EI, and R2 is equal to minus 221.698 upon EI. Let us compare that to the situation where you have fixed. What was the fixed case? Fixed case, R1 was equal to minus 666.67 upon EI, and R2 was equal to minus 150 upon EI. That is when fixed roller. This is hinge roller. So now let us look at what the effect of removing the fixity at this point to make it into a hinge. In other words, eliminating the restraint, the rotational restraint. What has that done to the actual displacement of the structure under the same loads? Remember, I mean, the loads for both the structures are identical, the geometry is identical. The only difference between the two structures is that in the previous case at C you had a fixed roller, and in the second case that we are dealing with right now, it is a hinge roller. So all we have removed is we removed the restraint of rotation, and see what that has done to the displacement shape. It has had a significant effect. Look at the rotation. The rotation has gone up significantly. And more interestingly, you see R1 was downwards when it was fixed. Now that you remove the restraint, it's actually upwards. Isn't it very interesting that just what kind of an effect? You would think that what have I done? I have actually just taken a support at one, and all I have done is removed the restraint, rotational restraint. But the whole displacement pattern, now the support at C, instead of moving down, is actually moving up, and the value is much larger. Okay, this brings us to a particular point, and that is that when I removed the restraint, what did I do to the structure? Think about it. When I put more restraints on the structure, what do I do to a structure? When I add restraints to a structure, I actually make the structure stiffer. When I make a structure stiffer, for the same load, what would you expect the displacements to be? Less, isn't it? Look at that. It's less. Okay? So now the point is, when I remove the restraint, I made the structure more flexible, and therefore the displacements have to go up, and they have gone up. So therefore the behavior of the structure actually is reflected in the results that you get. This is very, very important. Okay? So the displacements have gone up. Now I can put these displacements into the equations for the moments. These are the equations where MAB, MBA and MBC are in terms of R1 and R2, and since I know R1 and R2, okay, I can substitute into that equation, and when I substitute into that equation, what I get is this. MAB is minus 13.21, MBC is minus 57, and MBC is plus 57. What were they when it was fixed? This was minus 60, this was minus 90, and this was plus 90. what has happened to the member end moments? They've gone down. Okay? They've gone down. Why? Well, when I made the fixed roller into a hinge roller, what did I do? I increased the flexibility of the structure. Now, here is where I make the points that I have tried to make. When you make a structure, when you make a statically indeterminate structure more flexible, you increase the displacements. We've already seen that the displacements are significantly larger than in the fixed roller case. And B, you make the member end moments smaller. Why? Because the structure is more flexible, and therefore what it does is, when a structure is more flexible, it can actually displace to relieve stresses in the structure. And therefore when it can deform more to release the stresses, or in this particular case the member end moments, reduce. Okay? So therefore, stiffer structure, what do? When you make a statically indeterminate structure stiffer, you reduce the displacements, but you increase the member end moments. When you make it more flexible, why the member end? Because when you make it stiffer, it's less able to deflect, and so therefore the loads, the deflection is small, and the loads are essentially transferred through forces. When the structure is more flexible, okay, it can deform and relieve the stresses. Okay, so therefore the member end stresses are less. Does that mean that if you do not have a serviceability criterion? So now this is where I come into the design aspects. The design aspects, you have two aspects. One is to design for strength, and the two is to design for serviceability. Serviceability always puts a restriction on your displacements, and the strength is to essentially so that it can resist the forces that it's subjected to. Okay. Now, when you make a structure more flexible, what happens? Displacements go up. So if you do not have a serviceability problem, then you might think that, well, I get the displacements to go up and I get the moments to go down. Okay, so I can actually make the structure sleeker because it needs to resist less forces. But this is incomplete information. Let us look at what happens to the bending moment diagram due to these, and that is the next step that we are interested in. So we've got the member end moments, and therefore in this particular case, if you look at it, here the member end moment is 13.21, minus 13 is clockwise, minus 57.5 is clockwise, plus 57 is anti-clockwise, and so these are the member end moments. Now this is the joint B, this is the joint at B, this is the joint at A, and this is the joint at C. Okay, so now from this, if I take MAB, since it doesn't have any loading, the shears at this point are going to be equal to what? This into this is equal to this plus this. So the couple generated by the shear is going to negate this moment, and from that we get that HA is equal to this plus this upon 10. That's equal to 7.076. So that means HA is in this direction and the value is 7.076. Okay, in the previous case, what was this? 15. This becomes HC becomes 57.076. What was it before? 65. So we seem to be going in the same direction. Same direction meaning that the member end moments and the support reactions seem to be all less. Okay, so still we think that things are going to improve. Okay? But now since I have got this, I can actually find out the support reactions, and this is ultimately what the structure looks like. Once I have the support reactions, this becomes a statically determinate structure, and I can draw the shear force bending moment diagram for this. Okay? And if I do that, this is clockwise 13.21, this is 7.06, 100. Since this is a roller, the entire 100 comes here. And here, since there is no, it's hinge, there is no moment, there is only 57. Till now, structure is more flexible, the support reactions are less. We are seemingly, in other words, if your serviceability is not a criteria, making the structure more flexible by removing a restraint of support seems to make the structure much better. However, let's look at the bending moment diagram. The bending moment diagram, if I'll leave it up to you to do. Remember, I told you that I am not going to be doing equilibrium for you. Once I have got the support reactions, you should be able to generate the bending moment diagram, shear force diagram for any member. Okay, and I've drawn the bending moment diagram. This is the bending moment diagram here. The bending moment over here has to be 13.21 because that's the support reaction. The bending moment over here has to be 0 because at this point you have a hinge, so you cannot have a moment. And if you look at this, what happens here? What was this? 60 kilonewton meter. Kilonewton meter. This was 115 kilonewton meter, and this, which is 0 now, was 80 kilonewton meter. Now let's look at, from a design point of view, is flexibility good? What does this, as far as this member AB is concerned, it's good. It has actually reduced the bending moments significantly from the previous case. However, in this case, what's happened? In the previous case, this was 115. Now, this is 171.23. Significantly more. Significantly more. In other words, now the member BC, okay, up till now we were seeing, make it flexible. It's going to get much, much better as long as you do not have a serviceability limit. In other words, the rotation and displacement can be anything that it wishes to be. Okay? Then we thought that introducing flexibility was being wonderful because it was reducing all kinds of bending moments in the structure. But you have a problem. It has not. This particular one is more than 1.5 times, and this member BC has to be designed for what? It has to be designed for this. So in other words, you see what's happened. What's happened here is that making the structure more flexibility does indeed, making the structure more flexible does indeed increase the displacements and reduce the member end deformations, member end moments. However, if any structure has a load on a member, then this is not a good idea, because we'll see what happens. The maximum bending moment in the member goes up significantly if you have a member loading. Okay? So now if you look at this, would you say that increasing the flexibility of the structure makes it better? No. In fact, if you look at it, by restraining the rotation here and making the structure more stiffer, you may have increased the moments. However, you've made the moments much more even. You see the difference between this, and this, and this, and this. You see the lowest moment here is what? 60 kilonewton meter, and the highest 115. Here, lowest 13.21, highest 171. You know, there's a tremendous amount of bending moment variability, and therefore bending moment variability essentially implies that curvature goes up, and you might have actually cracking problems, etc., if you have a reinforced concrete. So therefore, by and large, increasing restraints in the structure is actually a good idea, of course, as long as you don't keep increasing it to a point at which what happens is displacement goes down and almost all the entire forces are transmitted. At that particular point, if you take restraints beyond a certain point, you reduce forces, okay, you reduce the effect of the loads, but the member end moments go up significantly higher, and you no longer reap any benefits of making the structure stiffer. So there is, therefore, the point that I was trying to make is that there is an optimum stiffness for a particular type of loading that good designers always look for. Okay, so ultimately that was my take on the behavior of structures. But as far as getting the solution is concerned, you can see that if you have a structure, then the displacement method, I'm now ending the entire discourse on using displacement method for a statically indeterminate structure. And I want to end it by going back through the steps. First step, determine the number of degrees of freedom of a structure, given all the restraints and constraints that you have. That's number one. Number two, once you've determined the number of degrees of freedom, you have to define the displacements corresponding to those degrees of freedom. Okay? 3, determine what each member is and write down the member and force deformation relationships. 4, take the kinematic relationship determine the kinematic relationship between the displacements corresponding to the degrees of freedom and the member end deformations. That is where the kinematics comes in. Then 5, now once you've got the kinematics, you can write down the member end moments in terms of the displacements corresponding to the degrees of freedom. Then 6, use the virtual work principle, specifically the virtual work displacements, to write down independent equations corresponding to each degree of freedom. 7, solve those equations for finding out the displacements corresponding to a particular loading system. 8, substitute those displacements into the member end displacement relationships to get the member end moments. Once you got the member end moments, 9, do equilibrium and find out the support reactions and the bending moment diagram, shear force diagram, whatever you have to do. And that's your analysis completed. Okay? Now, the next lecture is going to be my last lecture on the displacement method, where till now I've only looked at loading in the member. Now I'm going to look at other situations, other kinds of member loads, and finally, up till now I've only looked at flexural deformations and flexural member end force deformation relationships, and in trusses these are not valid, so I shall look at trusses briefly so that you can apply the displacement method for all types of planar trusses and planar frames. Okay, thank you very much. Bye.